Hello dear students, I am B.S. Pandey, your physics lecturer. Today we are in lecture number 16. Lecture number 16 of chapter 1, electrostatic unit. Okay, student, today we will study the application. Okay, application of Gauss law, and this is very important lecture, student. In 2018-2019, the question has been asked from this application. Okay, in 2020, there was a very conceptual question, the very simple question asked, but for 2021, this is very important. So the first application today we will take, it is the electric field due to infinitely long linear charge conductor. Okay, carrying charge, linear charge, you can say the non-conducting. I will spread the charge over the non-conducting, okay, body. So the first application, electric field due to long linear, that is the one dimensional, long linear charged non-conducting body, okay, or non-conducting wire. Here, student, we will use Gauss law to find the electric field. Suppose this is a conductor of infinite length, since we have been used the term very long, and it is charged uniformly. Okay, here lambda is the linear charge density, linear charge density. We have to find electric field at this point. Suppose at this point, so we will draw first a Gaussian surface of the same radius to enclose this elemental charge. Since this is infinitely long, we are taking a elemental length, okay, or the elemental charge. To enclose this elemental charge, we know that we need a cylindrical Gaussian surface. Okay, so we will use here a cylindrical Gaussian surface to enclose this wire. Now we have been enclosed this one. You can see, if you are enclosing this one, how the electric field lines will emerge out from the cylinder. Of course, the electric field will move in this way, radially outward, everywhere. Here also the electric field will be upward, here also the electric field will be upward. But the area vector at this point, these are the electric field, okay, electric field. Area vector over here will be in this direction. This is the area vector. Here the area vector will be in this direction. Okay, for this curved surface, the area vector will be considered as, if you are using this curved surface, the area vector will be considered along the r cap, radially outward. Student, already we have been discussed while solving an example. Okay, now using this Gauss law, we will find out the electric field due to this conductor. What are observation point? What is our observation point? This point is P. P will be our observation point. Observation point that we have to, at this point we have to find the electric field. This is our observation point. Okay, student. Now, according to Gauss law, we can write here the phi net is equals to E dot dA. Okay, close integral of E dot dA. So here the phi net is the three surfaces. To study the complete this Gaussian surface, we are having the three surfaces, 1, 2 and another this curve one. Okay, so the phi 1, phi 2 plus phi 3. Okay, my dear student. Now this one, the phi 1, suppose this one 1, this is 2 and third is the Gaussian, this curve surface. So for the 1 it is E electric field in upward direction, J dot A here minus I cap, plus for phi 2 again E J dot AI, this one, plus this area, curve surface area, it is, if the radius is R, then curve surface area will be how much? EJ, because for this curve surface the electric field will be again, it is EJ you can write, or the ER you can take, dot 2 pi R L, if L is the length we are taking. Okay, and the direction will be again the R unit vector or the J cap. So this is the total electric flux. Now student, here the J cap and I cap are perpendicular to each other, so the flux will be 0. Here the flux will be again 0. The flux you will get only for this surface, and this flux will be written as how much? It is E times 2 pi R L. Here the J dot R will be 1 because J and R are in same direction. It is not everywhere, but here where we are considering actually the point R and J both are in same direction. So E times 2 pi R L. This is our flux. Now we know that this phi can be also written as Q enclosed by epsilon naught. Yes, student, Q enclosed by epsilon naught. Now we have to find the Q enclosed. Okay, Q enclosed we have to find. So the Q enclosed will be, here charge is enclosed within the length L, and lambda is the linear charge density, and we know that the linear charge density if is given, then at particular length we can find the charge by multiplying this lambda. So the enclosed charge we can write here the lambda times L. Okay, and this is the enclosed charge that we have to put over here, and this phi is equals to this phi. So we can write here the E times 2 pi RL, it is equals to Q enclosed, which is equals to lambda times L over epsilon naught. I hope you are getting. Now we have to find the electric field. We are near our result. L will be cancelled out. Again, if there was any question coming in your mind, sir, why we are taking here the length L, why not 2L or 3L? So again, try to focus. Here nothing is to take for this length, it will cancel out. Okay, and it will not affect your answer. So lambda by 2 pi R epsilon naught, lambda by 2 pi r epsilon naught, and this is the electric field due to linear, okay, uniformly charged linear non-conducting wire. You can simplify this one as also. Here you are having 2 pi epsilon naught, 2 pi epsilon naught. If it is 4 pi epsilon naught, then you can write as the k lambda. Okay, so try to convert this one in k multiply by 2, okay, numerator and denominator both, because it will not affect the answer. But this will be the 4 pi epsilon naught, and this E will be written as 2, and 4 pi epsilon naught will be k, and this lambda by this epsilon naught. So this can be also written as 2k lambda by epsilon naught. It is very easy, student. You can see clearly, if you are moving away, what is changing. If you are moving away, what is actually changing? K is constant, epsilon naught is constant, and lambda is also constant. If you will ask to draw the graph between E and R, if this R is increasing, how the electric field will change, then you can draw easily that how this electric field will change. Okay, here actually I think R is, we haven't taken a, sorry, R it is here na? Now try to draw the graph. Actually epsilon naught we have been taken in K na, R was left. Now the graph of E versus R, for which one? For linear non-conducting wire. Okay, this will be asked. This is the conductor, charged conductor, actually diagram little bit I have been changed to understand the graph. Okay, now this is the radius R, it is 0. We will use electric field on this axis, and R on this axis. This R can be written as in meter, and this electric field can be written as a Newton per coulomb, okay, over the y-axis. As you are moving away from the conductor, you can see it is 2 constant, k constant, and lambda is also constant, but this E is inversely proportional to R, and the graph will be this way. But remember student, don't touch this graph with the y-axis, because at y-axis the R will be 0 and you will have the electric field, which is incorrect. Over the conductor, any conductor cannot experience electric field itself. So if R is 0, electric field will be 0. Okay, and just after the R, the electric field will be maximum. Try to use this converse. Okay student, so this was the application. In first application we have been studied how to find the electric field due to this charge linear conductor. Okay, now the next application, student. In your NCERT there is 2 questions, there are 2 numericals you can solve now, student. Now the second application, my dear student, second application, you have to find the electric field due to uniformly charged thin sheet, and this thin sheet will be large, very large. Okay, you can use the metal plate also, and the thin sheet you have to use over here to find the electric field. Suppose this is thin sheet. It is charged uniformly. What are the quantity you are having? You are having sigma. It is the surface charge density. Surface charge density. If you will use a elementary surface area as A, elementary surface area as A, surface area, then the Q enclosed you will have sigma times A. Okay, we will use this concept. Now, what is the meaning of this thin sheet, student? So the thin sheet, it means this positive charge will have the effect at both sides of the sheet. This one is actually, we have to find electric field at this point. Okay, so again, since it is going to infinity, it is going to infinity, very large, so all the sides it is moving for the infinity. For simplicity, we'll take a Gaussian surface, and the Gaussian shape of the Gaussian surface we will take here the cylindrical. Now again, you can ask, or you can create a question from yourself even, why this shape of Gaussian surface is cylindrical. Okay, at here we have to find the electric field. Since this is thin sheet and the charge having the effect at both the side, so the Gaussian surface will be considered at this side also. So at this side, the Gaussian surface we are considering in this way, and this is the cylindrical body. If this is the area A, okay, this is also the area A. The A already we have been considered. Now find the direction of electric field at different surfaces. Here the different surface we are having the three surface. 1, 2, this is the plane surface, and 1, it is the curve one. For this curve one, if area is A dash, suppose, what will be the direction of electric field? Direction of electric field will be in this direction, and this will be perpendicular. So the flux will be 0. That's why I'm not giving the value to this curved surface area, but in our calculation we will represent the curved surface area also. Here the electric field will be, since it is the positive charge, electric field will be outward. Here the electric field will be, since the positive charge that side, the electric field will be again outward. Okay, while you are drawing the diagram, you must have to represent this all much. Okay, in your examination you will get the marks for the diagram also. Whenever you are asked to give the answer in board examination, try to make the diagram with its maximum possibility. Where the diagram is being not asked, you can use to make the diagram. Okay, that would be the beneficial. Now we are going to find out the electric field. Here we have to find the electric field over here. We can change the distance also. Suppose this distance is n1. It is nothing about to take. Since this curved surface is not giving the flux, so it is not mandated to take the length, this one. Now the net flux, again we are having the three faces, or the three surfaces, 1, 2, 3. We can write here the flux due to this surface as EA, but this E is also in this direction and area is also in this direction, so both will be positive, plus 2, the second one, this area, electric field in this one, and area is also this one, so again EA, plus for this surface the electric flux is 0 and it is 2EA. Okay, so this is the flux equation 1. This is the net flux, and we know that according to Gauss law again, this flux should be equals how much? Q enclosed by epsilon naught. Okay, so we can write here the Q enclosed, how much it is. The Q enclosed we have been written already, the sigma times A. Why Q enclosed, sir? Because this area is equal to this area also, and this area encloses the charge, how much? Sigma times A by epsilon naught. This is the second equation, and both the flux are equal, equation 1 and 2. So we can write here that 2 times EA is equals to sigma A by epsilon naught. This A will cancel out, and E can be written as sigma by 2 epsilon naught. Sigma by 2 epsilon naught. So this is the mathematical expression for the electric field due to thin sheet. Remember, this is the thin sheet, and this is very important because the same you will have to use in capacitor also. Now the student try to draw the graph. Now can you note down? So we are having the electric field E sigma by 2 epsilon naught. Okay, the graph E, and this is the length, suppose it is the x. You can see this formula E is sigma by 2 epsilon naught. Sigma is constant, epsilon naught is constant, 2 is also constant. So this E is constant and it will not depend upon x, so it is independent. The graph will be in this way. At this point the electric field the left, otherwise the graph will be in this way. Okay student, so this will be the shape of the graph. Now student, third application we'll use to find the electric field due to charge thick sheet. This is the third application. Okay, thick sheet. For this thick sheet I am not going to solve this one completely, you will solve by yourself, but I am giving you the trick or the small hint. Thick sheet, here this is the charged sheet. If you will spread the charge on this thick sheet, since it is thick, so charge will not move and this charge will not have the effect at the other end. We have been spread, if we have spread the charge at both the surfaces, then this is the different case. Otherwise, if we have spread the charge uniformly with the surface charge density sigma, already we have been studied in last division, surface charge density sigma, then the charge will not affect, charge has no effect at the second surface. So for this particular surface we are taking here the Gaussian surface as cylinder, again of radius r. Okay, and the electric field will be in this direction. Here if we are considering elemental surface over here as A dash, the electric field will be here, electric field will be in this direction, it is E. Again the area vector and electric field are perpendicular to each other, but in this case the Gaussian surface will not move out because the charge will have the effect just inside. So we can draw here the Gaussian surface inside this particular, but not outside the sheet, just inside the sheet we are making here the Gaussian surface, just inside. Remember, it is just inside and it is not outside, so we will have only one surface. You will get the answer, student, as the E equals to sigma by epsilon naught, and try to derive this by yourself, student. Okay, and now the fourth application, electric field due to charged cell. If you will find fourth, E due to uniformly charged cell. Okay, खोखला. So it is uniformly charged of radius r with the surface charge density sigma. We'll try to find out the electric field outside the sphere over here at the surface of the sphere and inside the sphere, that is the cell. Here the case 1, outside the sphere, outside the cell. If this is the distance x, then we have to draw a Gaussian surface of radius x. We know that without drawing this Gaussian surface we cannot obtain, and the electric field must be obtained at this Gaussian surface. Take a elemental surface area. Suppose the area is A, okay, and the radius is x. Here the area is A. For this charge, the electric field will be in this direction only. Using the Gauss law, we can write here, using Gauss law, we can write E dot dA is equals to Q enclosed by epsilon naught. Okay, now we have to write the Q enclosed, and this Q enclosed will be how much? The sigma times total area. It is area of the sphere 4 pi r square. Okay, since the charge is spread over this r square, not over the x, so sigma 4 pi r square. This is the Q enclosed. So E dot A dA, it is equals to Q enclosed, that the sigma times 4 pi r square over epsilon naught, Q by epsilon naught. Here the E times dA. This dA is the elementary surface of this one. You can write the dA, elementary surface of this one. And by integrating this dA, what you will get actually 4 pi x square. Okay, sigma 4 pi r square over epsilon naught. This 4 pi will be cancelled out. Okay, so you will have E as sigma r square by x square epsilon naught. Sigma by epsilon naught r square by x square. Since this r is constant, we are not changing the radius. R is constant. If we are finding the electric field over here, then we are changing the x only. If we are finding the electric field over here, then changing the x only. So we can also write a converse over here. The E is inversely proportional. Sigma is constant, epsilon constant, r is constant, inversely proportional to x square. Okay, x square, and that will be the helpful to draw the graph. Now case 2, we can erase this one. Case 2, at the surface, at the surface, remember, if we are moving at the surface, the Gaussian surface enclose this cell completely, and Q enclosed not going to change. Remember, if Q enclosed is not going to be changed, it means the formula you will get here the same. It is E times E dot A. Actually, I am writing here the E times 4 pi, or let me write E dot A dA is equals to sigma times the charge. It was 4 pi r square over epsilon naught, and E and dA how much? If you are at this point, then the surface area again will be 4 pi r square sigma 4 pi r square by epsilon naught. It will be cancelled out, and then you will have the electric field as sigma by epsilon naught. Okay, my dear student. Now the third one. Okay, this is at the surface. Now third one, case 3. Case 3. Case 3, inside. As we will move inside, remember, drawing the Gaussian surface inside, there will be no charge inside the Gaussian surface. So Q enclosed will be how much? It is 0. So the electric field will be also 0. It is quite obvious, because you will use E dot D equals to Q enclosed by epsilon naught. Since Q enclosed is 0, then E will be 0. So inside the cell, the electric field will be how much? 0. Now you will be asked to draw the graph. So you can draw the graph easily. From center, I am taking the reference at this one. E from center O, and here the X. Okay, at the center the electric field is 0. Here it will be 0. Here it will be 0. At the surface you are getting actually electric field. And how much it is? At the surface you are getting the electric field. It is sigma by epsilon naught. Try to recall sigma by epsilon naught. After that you are getting the electric field, and it is varying with this equation, E inversely proportional to x square. So you will get this equation, and this is the graph of electric field due to cell versus the separation. Okay students, so these are the important application. It was in the next lecture we will do some numerical question on the basis of this all the application. Students, thank you very much.